Have you ever stopped to think about how your ideas, your clicks, your every command gets translated into a language that a computer can actually understand? Well, today we're going to pull back the curtain and dive into the number systems that are the true foundation of our digital world.
And that right there is the big question, isn't it? At their very core, all digital electronics, your phone, your laptop, everything, are just billions of tiny switches that are either on or off, a 1 or a 0. So if they only speak this super simple two-word language, how do we get them to do all the complex, amazing things they do?
So here's our game plan. First, we'll introduce the main players, the different number systems. Then, we'll dig into why the computer's favorite language, binary, is a real pain for us humans. After that, we'll reveal the brilliant solution. I'll show you exactly how to do the translations yourself. And finally, we'll connect all of this to the real world. All right, let's jump in and meet the 4 key languages, or number systems, that really make computing possible. And you know what? You're already an expert in one of them.
First up is decimal, or base 10. This is the one we all learned in school. It's our everyday language for counting, using 10 simple digits, from 0 all the way to 9. It's just how we humans are wired to see the world.
Now for the language that machines actually speak, binary, or base 2. And as the name implies, it only uses 2 digits, 0 and 1. Think of it like a light switch. 0 is off and 1 is on. Every single thing on your computer, every photo, every song, every line of code, is at its most fundamental level just an incredibly long string of these 1s and 0s. Next, we've got the octal system, base 8. You can probably guess this one. It uses 8 digits from 0 through 7, so you'll never see an 8 or a 9 in octal. Now, this might seem a little random, but trust me, we're going to see why it's so incredibly useful in just a minute. And finally, we have hexadecimal, or hex for short. This one, base 16, is where things get interesting. It uses our familiar 10 digits, 0 through 9, but it needs 6 more symbols to get all the way up to 16. So what does it do? It just borrows the first 6 letters of the alphabet. So in hex, A stands for 10, B is 11, and it goes all the way up to F, which represents 15. This chart really helps it all click into place. Just look at how the same value is written in these different systems. Up to the number 7, everything looks pretty much the same, but look what happens at 8. Octal has to roll over and becomes 10. And then when we hit decimal 10, hexadecimal switches to letters and we see our first A. It's a great way to see these different languages side by side. Okay, so if computers speak binary and we speak decimal, why on earth do we even need octal and hexadecimal? Well, the answer comes down to a really big communication gap between us and our machines. I mean, just look at this number on the screen. Could you tell me what it is just by glancing at it? Could you remember it long enough to type it out without making a single mistake? Probably not, right? Binary is perfect for computers, but for our human brains, it's just, well, it's a nightmare. It's long, it's confusing, and it's so easy to make a mistake. And this quote just nails it. We need a better way. We need a way to represent these long, messy binary numbers in a format that's more compact and friendly for us humans. We need a shorthand. And this is where octal and hexadecimal come in to save the day. You see, they're not just some other way to count. They are brilliant, elegant tools specifically designed to make binary manageable for people like you and me. And the magic behind it is actually some really simple math. Check this out. 2 to the power of 3 is 8. That means any group of 3 binary digits can be perfectly represented by a single octal digit. And 2 to the power of 4 is 16, which means any group of 4 binary digits can be represented by a single hexadecimal symbol. It's a perfect one-to-one mapping. It's so clever. And this is that aha moment. So we take that long, ugly binary string from before. All we do is break it into little chunks of 4. Then we just look up what each chunk means. 1110 is E in hexadecimal. 1001 is 9. And 1010 is A. And just like that, that giant 12-digit binary mess becomes a simple, clean 3-character hex number, E9A. So much easier to read, to write, and to remember. It's a total game changer. Okay, so we get why these systems exist. Now, let's roll up our sleeves and figure out how to actually do it. How do we take our normal, everyday decimal numbers and translate them into these other languages? The main technique we're going to use is called successive division. Now, it sounds a little technical, but the idea is actually super simple. You just take your decimal number and you keep dividing it by the base you want to convert to. So you divide by 2 for binary, 8 for octal, or 16 for hex. The only trick is you have to keep track of the remainders. Let's work through an example together to really see this in action. We'll take the decimal number, 348, and we're going to convert it into binary, octal, and hexadecimal. Okay, for binary, we're going to divide by 2 over and over again. So 348 divided by 2 is 174 with a remainder of 0. Then 174 divided by 2 is 87, remainder 0. You just keep doing this all the way down until your main number is 0. Then, and this is the most important part, you read those remainders from the bottom back up to the top. And there's your binary number. For octal, it's the exact same process, but this time, you guessed it, we divide by 8. We take 348, divide by 8, take that result, divide by 8 again, and so on. Again, we read the remainders from the bottom up, and we get 534 in octal. See? It's the same pattern. And finally, for hexadecimal, we divide by 16. So 348 divided by 16 leaves us with a remainder of 12. But hold on, we can't write 12. What do? We have to remember that in hex, 12 is represented by the letter C. We keep going with the division, and once again, reading those remainders from the bottom up gives us our answer, 15C. So we've gone through the what, the why, and the how. But you might still be thinking, okay, that's cool, but where does this actually matter? Let's talk about where you'll see this stuff in the wild. The truth is, these number systems are the hidden language of almost all technology. You know when you're on a website and you see a color code that starts with a hashtag, like hashtag FF5733? That's hexadecimal defining a color. When programmers are debugging low-level code, they're looking at memory addresses in hex because it's so much easier than binary. And if you've ever worked with a Linux system, the file permissions are all set using Octal. This isn't just theory. It's the practical, hands-on foundation of our digital lives. You know, understanding these number systems is really like learning the basic grammar of the digital universe. It takes you from just being a user of technology to someone who actually gets how it works on a deeper level. So the real question is, now that you've got a key to understanding their language, what new possibilities are you going to unlock?